So good morning, I'm Eugen Miculec. I am a forecasting meteorologist for the Romanian Meteorological Administration. And today I will give a short presentation about the use of technology in meteorology with emphasis on how computer science is impacting weather prediction. I guess everyone is familiar with weather-related information, be it a weather map, a satellite image, weather radar images, or regular mobile phone weather apps. And perhaps we are all aware of the importance of precise weather predictions, even though we might not be all familiar with how weather forecasting actually works. One definition of weather forecasting says that it's the application of technology and science to predict the state of the atmosphere for a future time and a given location. So as the definition indicates, science and technology are the core of meteorology. And human interest in predicting the evolution of weather existed since ancient times, and first rain gauges developed more than 2,000 years ago. And they were followed by development of other measurement tools and theories. But the actual pace of development accelerated during the 20th century. And in 1917, a Norwegian, Wilhelm Birknes, introduced his theory describing the formulation of wave cyclones and the polar front, and laid the foundations for modern method of weather forecasting. So this laid the foundation of current meteorology. And since then, in the 20th century, technology developed in an accelerated pace. And in the 20s, so about 100 years ago, the basis for mathematical prediction of atmospheric circulations was laid, but the actual theory was only put into practice when the high-speed electronic computers appeared, so in the late 40s. And in the mid-50s, 1955, the first computer forecasts were made operational. Since 1959, meteorological satellites are providing an overview of the atmosphere over cloud patterns and are serving, among other things, as early warning and detection systems for severe weather phenomena. Information gathered by Earth orbiting satellites are being used in computer models to predict long-term and short-term meteorological events, such as extreme storms, convective storms. But at the moment, the basis for weather forecasting are the numerical weather prediction models. And numerical weather prediction data are the form of weather model data that is most familiar with us on a day-to-day basis. And the traditional already traditional forecasting process employed by most national meteorological administration involve forecasters producing weather prediction products using those numerical weather predictions outputs. So a definition would be that it's a model that is quantitatively predicting the evolution of atmosphere state, determined by temperature, wind, humidity, and pressure, among others, through numerical simulation. And the current atmospheric state is determined by the interpolation of various observational data on regular space model grid points. So the assimilation of data of observation is introduced in those computerized models. So NWP is a method of weather forecasting that employs a set of equations that describe the flow of fluids. These equations are translated into computer code and use governing equations, numerical methods, parameterizations, and other physical processes, and combined with initial and boundary conditions before being run over a geographical domain. almost every step in the NWPs includes omissions, approximations, compromises. Those are the basis for. These are one of the basis for the errors in numerical weather prediction. The idea of those models is to give to give the state of the fluid, of the atmospheric fluid at a given time, and use the equations of fluid dynamics and thermodynamics to estimate the state of the fluid at some time in the future. So an atmospheric model is a computer program that produces meteorological information for future times at given locations and also altitudes on many altitude levels. Within any modern model, there is a set of the equations known as primitive equations that are used to predict the future state of the atmosphere. These equations, along with the ideal gas law, are used to determine the evolution of the density, pressure, potential temperature, and wind velocity, direction, and so on throughout time. The equations used are nonlinear partial derivative equations, which are impossible to solve exactly through analytical methods. So numerical methods obtain an approximative solution, numerical approximative solution. These equations are initialized from observation data and from the outputs of former steps, and the rates of change are determined. These rates of change predict the state of the atmosphere a short time into the future, and the time increment for this prediction is called a timestamp. Time step. This future atmospheric state is then used as a starting point for another application of the predictive equation to find new rates of change. And in turn, the new rates of change predict the atmosphere and yet another further time step into the future. This time stepping is repeated until the solution reaches the desired forecast time. The length of time step chosen within the model is related to the distance between 2 points of the computational grid, and is chosen to maintain a numerical stability, a so-called numerical stability. Time steps for global models are in the order of tens of minutes, while for high resolution models, regional models, timestamps are between 1 and 4 minutes. The global models are run at varying times into the future. For example, the UK model is ran for 6 models into the future. The ECMWF, the European Center for Midterm Weather Forecast, is ran for 10 days into the future, and while the American Global Forecast System model is run for about 16 days into the future. Some meteorological processes are of too small scale or too complex to be explicitly included in a numerical weather prediction. So a parameterization is performed, which is a procedure for representing those processes by relating them to variables on the scales and on scales that the model resolve. For example, the grid boxes in weather and climate models have sides between 1 and 5 kilometers and 300 kilometers in length, the slides. and a typical cumulus cloud has a scale of less than 1 kilometer, and it would require a grid even finer than 1 kilometer in order to be physically represented. Forecasters have always understood that it's very important to analyze multiple numerical weather prediction forecasts in order to get a reliable forecast because of the errors and uncertainties that each model contains. And one way to do this is to compare different numerical weather prediction forecasts, so different models, and they might compare regional to global models or compare forecasts from delivered by different forecasting centers. They can also do this by comparing different model runs from the same model, looking how new observation change the model forecast outcomes over time. And those are the ensemble forecasting. Ensemble prediction is a relatively new tool for operating forecasting. So that allows rapid and scientifically based comparison of multiple model forecasts. Ensemble products like the spaghetti diagrams here use various statistical and graphical methods to combine multiple model runs, each based on slightly different initial conditions or using slightly different model configurations and parameterization. By doing so, they can include information about the level of uncertainty, the most likely forecast outcomes, and probabilities of those outcomes. It is clear that that weather and climate modeling are among the most power-hungry use cases for supercomputer. As in many cases, the models are simulating the atmosphere of the entire planet, and at a very high granularity and regularity as possible. In this sense, the supercomputers employed in meteorology are one of the most powerful supercomputers in the world. For example, the next UK Met Office supercomputer will be in the range of 1.5 million cores and about 60 petaflops. And yeah, the main problem here is the energy consumption related to running those supercomputers. Actually, the next supercomputer at the UK Met Office will run on 100% renewable energy. But still, there are, beside the energy consumption problem, is also the time of integration. Integrating those models. So that's why weather and climate research community is increasingly aware of modern deep learning technologies and try to adopt them in order to solve specific data analysis, numerical modeling, post-processing problems, and some deep learning concepts have already been successfully applied to problems related to weather forecasting. However, the few existing attempts to replace entire numerical weather prediction with a deep learning system have been limited to short-term forecasting, up to 24 hours or less, and used a rather limited subset of available meteorological data. So there are a number of challenges we need to be overcome before a complete end-to-end deep learning weather forecasting system can deliver results comparable to current numerical weather prediction. A problem is related to the purely data-driven model, which may fail to adhere to the underlying physical principles, and thus it could generate false forecasts, as it lacks the understanding of the fact that every atmospheric process obeys certain physical laws described by the conservation of momentum, enthalpy, Newtonian physics. So a vibrant area of research is incorporating those physical law in the machine learning models. As the domain is very large, as the Earth is very large, the domain for global models is very large. Apart from being very laborious, developing a representation model of the Earth weather and climate systems brick by brick, as it is done by the numerical weather prediction, isn't actually achieving the accuracy that one might imagine. So despite the computing firepower behind weather forecasting, behind the numerical weather prediction, most models still remain at resolution of about 10 kilometers that cannot represent clouds and other chaotic atmospheric dynamics. And occasionally they opaque interactions to further model outputs. So, and on the other side, we have a great amount of observation, of meteorological observations. For example, the European Center for Midterm Weather Forecast is gathering hundreds of millions of observations into their site every day. And this data is collected over the last several decades, and there are hundreds of petabytes of weather and climate models there. So we have a very complex nonlinear system and a lot of data. So there are a lot of potential applications for machine learning in weather modeling. And machine learning, actually, there are applications are actually already spread all over the entire workflow of weather prediction, from observations, data assimilation, numerical weather forecasting, the pre-processing of numerical weather forecasting into the dissemination, and could across those areas, machine learning could be used for anything from weather data monitoring to learning the underlying equations of atmospheric motions. As mentioned earlier, much of the modern weather forecasting focuses on ensemble methods, where a model is run many times in order to obtain a spread possible scenarios. And deep learning could be employed also here in order to correct the ensemble spread, calculate for a relatively maybe a small number of ensemble. Nevertheless, there are still reservations about deep learning. In fact, about the possibility of deep learning replacing the entire workflow of numerical weather prediction. And the two core arguments in this regard are the lack of explainability of the deep learning networks and the lack of physical constraints. And some skepticism is also because of the fact that so far researchers have experienced with rather simple machine learning models, which were not suited to capture the complexity of meteorological data and feedback processes. And furthermore, deep learning methods are needed to cope with the complex statistics, multiple outputs, different noise sources, and high-dimensional spaces. So neural network topologies that not only exploit local neighborhood, but also the long-range relationships are needed. But the exact cause and effect relations between variables and are not clear in advance and need to be discovered. So when reflecting on the ultimate goal of replacing computationally expensive numerical weather predictions with deep learning algorithms, it's important to reconsider the objectives of weather forecasting and carefully define the requirements, which must be met by any potential alternative method. Because certain criteria which we consider as a granted, as a good weather forecast, may be in fact a preconception, which are simply resulting from our experience with numerical weather prediction and might not be applicable to weather forecasting systems, for example, those based on deep learning. So, well, the question if machine learning can replace core functionalities or even the entire forecasting system, this one is still has a still doubtful answer, and machine learning seem still they seem suited for a particular part of meteorology, that is nowcasting. And because of the chaotic character of the atmosphere and the fact that running a numerical weather model does not satisfy the time constraints, nowcasting at the moment mainly relies on the experience of operational meteorologists. So in this context, machine learning could be a suited approach, as the problem might be addressed as a computer vision problem, estimating the evolution of meteorological phenomena from a sequence of input data, which is the problem addressed by the colleagues from WEMIL team, and they will further present the results